Welcome to this episode of the Structural Engineering Channel podcast, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their career and lives.
In this episode, we are talking to Matthew J. Bandelt, Ph.D. in PE. Matthew is an assistant professor and associate chair of graduate studies in the Department of Civil and Environmental Engineering at the New Jersey Institute of Technology. He will be talking about the use of emerging concrete materials such as ultra-high performance concrete in projects and how they test these materials to evaluate its performance.
I'm your co-host, Matt Picardle.
And I'm your co-host, Kara Green. Now let's jump into the conversation of the week with Matthew Bandelt. Matthew, welcome to the show. I know for myself, there's always a little bit of ambiguity of professionals in the educational space, and I am so excited to speak with you and hear your take on some of the research you're doing. In your own words, can you please tell our listeners a little bit more about what you do on a daily basis at NJIT?
Sure. So thanks for having me. So as a professor, there's basically three things that I do and my colleagues, whether it be at NJIT or other universities. So obviously, most people are familiar with what we do as a teacher. So in my role, I teach undergraduate and graduate students topics related to structural engineering, mechanics, and materials. And this semester, I'm primarily teaching undergraduate reinforced concrete design. And it's been great interacting with them on campus again. So we've been remote, but now we're back on campus. Then the second component is research, which really drives kind of probably, I would say, most of my day-to-day work. And my research is on the application of new concrete materials with applications to structural engineering. And in this area, we study mechanical, structural, and durability behavior of emerging concrete materials and their application in the built environment. And we do this through numerical simulation and experimental testing. And then the third component to my job is really kind of service, and that's service to both my institution and then the professional community as well. So at NJIT, that involves advising students, student groups, participating in department, college, and institutional committees. And then in the professional community, it means sort of peer reviewing scientific publications before they go out and get published, contributing as kind of an expert in professional organizations, and then doing outreach to help bring research to practice. So those are kind of the three main components to my job.
Awesome. Thanks, Matthew. I know your research is based primarily in the field of ductile concretes and even materials such as ultra high performance concrete. Can you go into more detail about what is ultra high performance concrete? I know that's I've heard that used, it's also incorporated in the ACI codes, but I personally haven't had the chance to use it, but I hear it going around in the industry. So could you tell us more about what that is?
Yeah, so these materials are kind of rapidly becoming used, like the growth rate is sort of becoming exponential, but we study a range of different concrete materials that basically have high ductility. And we investigate how they can be used in structural and then durability related applications. You mentioned one material, ultra high performance concrete. It's sometimes referred to as UHPC for short. And UHPC is a class of concrete materials with very high performing mechanical properties, which can also improve its durability behavior as well. In compression, UHPC has strengths in the range of like 22,000 PSI or higher. So they're kind of very high compressive strength materials. And then in tension, the materials, they generally incorporate fibers. And those kind of fibers, what they do is they increase the tensile strain capacity. So in a UHPC system and other types of ductile concrete materials, you can get tensile strain capacities that exceed the yield strain of steel. So basically you could have a concrete that can deform compatibly with steel up to or beyond the same level that steel yields at.
Oh, cool. I just wanted to comment. That was cool just because it was for our listeners, if you don't deal with concrete too much, Matthew said 22,000. I typically work for most projects, maybe 5 to 6,000.
Yeah,
But that's how ultra is, and it's
yeah,
also good in tensile strength as well. So that's cool to hear.
yeah. So it's much higher strength, and then it's a much higher kind of deformation capacity or strain capacity. For UHPC, the high compressive strength is primarily derived by kind of really tight particle packing of the particles that go into concrete, and it's kind of highly engineered gradation of mixture constituents. In tension, so as I mentioned, the UHPC and these other ductile concrete systems derive their ductility through fibers. And those fibers might be on the order of magnitude of, say, a half inch long to 1 inch long. And they might be kind of anywhere in width from like the width of a couple of strands of hair to like the tip of a pen or something like that. They take up somewhere in the range of 1 to 2% of the mixture by volume, and then they sort of have a mechanical response that's either kind of elastic plastic or even strain hardening behavior. So in tension, it's very different than what you're used to kind of thinking of concrete.
That's great information. And as someone who just learned about non-ductile concrete for, I guess, the West Coast, it's very interesting to hear about ductile concrete, especially considering the fact here in Texas, or what I'm aware of around concrete, is it's an extremely brittle material. So can you explain a little bit about how ductile concrete materials can work to improve like seismic performance of structural systems and how that will impact? So for Matt, who designs likely in seismic areas, what that would look like?
Sure. So broadly speaking, researchers have been investigating these ductile concrete systems for quite a while in a range of seismic applications. So Matt, these might involve like plastic hinge regions, beam column joints, coupling or link beams that link together shear walls, and there's other applications as well. Effectively, they have two advantages to traditionally reinforced concrete members in terms of seismic design. So the first is when they're properly engineered, they have very high rotational capacity in plastic hinge regions for seismic applications. So this primarily happens because they don't fail at the same like curvature or rotation that an ordinary reinforced concrete member would fail at. And so instead reinforced concrete loses its capacity in flexure when it fails in compression. So you're used to designing members to behave like that. With these ductile concretes, they're so tough in compression that when they fail in flexure, that compression side stays on for sort of so long that it winds up failing in tension. So you get really high rotational capacities that can really increase the strength and ductility of components. And then the second advantage is it really has excellent shear performance. So in seismic design, shear demands can significantly kind of influence your design decisions. And so in traditional concrete, you develop those diagonal tension cracks, and then you rely on stirrups or confinement reinforcement to carry the stresses. And with the ductile concretes, because you have those fibers in there, they restrain the crack opening and thereby kind of increase the shear stresses and shear deformations. Recently, my research group has been using numerical models to help understand how we can design entire buildings with ductile concrete systems. And we've found really promising results. So for example, we found that you can reduce like the probability of collapse under a maximum considered earthquake by as much as 40% when you use these ductile concrete materials. And you get this advantage while actually using less concrete material because the strength is so high, you can reduce section sizes, and so you can have increased performance all while sort of reducing the amount of concrete material you're using in a building. So these have been used in sort of select applications in the field, but I think that will grow over time.
Yeah, that's interesting. In terms of, because I'm thinking about like performance-based design or nonlinear analysis, is it pretty much well recorded on the behavior for in terms of like if you do like a hysteretic diagram? Because I'm wondering about the tensile strength. It seems like there's going to be more tensile strength than regular concrete. Does that is that included in like the behavior? I guess that
Yes.
was
So
just
if you
something
were
I
doing
was wondering about.
like a performance-based design and you were if you were doing like a spring hinge or something like that to capture the behavior, you'd sort of have to update that hysteretic model to account for basically the added strength that you get in tension and then the added ductility. And so that's where some of my research has been recently, so that a practicing engineer could go and figure out how to recalibrate those, or I guess I should say reuse those models and account for the increases in behavior that you'd have for performance-based engineering.
Cool. How does the concrete impact the constructability or even the reinforcing in detailing in projects?
Yeah, so I guess kind of two ways that can happen. First, in like seismic related matters. So the ductile concrete systems, they have the potential to significantly reduce the amount of confinement reinforcement you might need. So like in seismic detailing, you can have a lot of rebar that comes together at these regions where you expect damage to occur. And you have the potential when kind of properly re-engineered to go and potentially remove some of that reinforcement or relax the spacing, because you're relying on now fibers to carry those stresses and deformations. And so that can significantly reduce spacing that you might need in stirrups or other areas. Outside of seismic design in the transportation sector, there's a lot of transportation agencies that we've seen that have used these materials, and they're using it in a lot of accelerated bridge construction applications. So a lot of owners and engineers are trying to use these materials to make connections simpler. So for example, taking like precast concrete elements that would normally need long splice lengths or long embedment lengths, and if you were using a traditional concrete pour, and instead if you use like a UHPC or similar type of system, you can significantly reduce those lengths, which it just makes it easier to go out in the field and use kind of precast elements in combinations with these higher performing elements that really speed up the construction. So those are kind of two examples of where these could be used.
And just to clarify, so you're saying that some of the benefits for transportation infrastructure is just necessarily speed, because, right now, obviously, there's the huge infrastructure bill that is currently under review on whether or not it will be released. Like when you say high performance concrete for the precast units for any sort of bridge construction or roadway construction, are you saying that speed is the only thing? Because when I think, or from what I'm hearing about high performance concrete, is that, it also kind of helps with maintenance. Would that not also be the case?
Exactly, yeah. So there's actually, when we talk about these ductile concretes, there's really two kind of benefits. So the first is, the potential for increasing speed and just making things easier to build. The second is related to durability. And so basically what happens with these systems, you have good packing, good gradation of the material. On the tension side, you can really limit the crack widths that develop. And so you get like these really fine cracks that develop. And so what that does is it slows down the rate at which water and other kind of aggressive substances move through a system. We have a few kind of ongoing studies, one with the New Jersey Department of Transportation, one with the US DOT Region 2 University Transportation Center program. They fund research in this area. And what they're looking at, or what we're looking at through these projects is related to improving the corrosion performance of our transportation infrastructure. And so as part of this, we're looking at kind of how different systems with varying mixture constituents, mechanical properties, and ultimately cost perform under these aggressive environments. These projects have been really interesting to me because, prior to a few years ago, my primary background was more in the structural mechanics area. And then more recently, I've moved into durability related research. And it's given me the opportunity to work with some really smart colleagues and expand my own skill set. And so that's one of the fun things about being a professor and doing research is you get opportunities to work in new areas. But to the short answer to your question is yes, there's applications that relate to construction speed and simplifying construction, but then also applications that relate to durability as well.
Thanks, Matthew. I'm wondering how you guys test this ultra high performance concrete. To me, it seems like you'd be just crushing concrete. Is that how it is out in the lab, or how do you test these things?
Yeah, so my lab is called the MATS lab, and it stands for the Materials and Structures Lab. Now, coincidentally, my colleague and I, my colleague is named Matt as well, and we both started at NJIT at the same time, but we sort of did a play on names. But we work together a lot on projects that sort of merge the space between material, behavior, and structural applications. So we have a range of different kind of testing capabilities. So we have structural testing that is used to kind of evaluate the behavior of individual components. So we might test beams or columns or other elements subjected to monotonic or cyclic loading. Right now, we've got a setup that's kind of in place for looking at how different factors can influence plastic hinge behavior with these materials. We combine that structural testing with a lot of numerical simulations. So, experimental testing is expensive. It's necessary, but it is expensive. And so we can use numerical simulations to sort of supplement the experiments that we do. And so we do a lot of fine element work as a tool to understand and supplement what we see in our experiments. So this might involve, building numerical models to predict material or section level behavior, and understand trends that we see in the experiments that we can't necessarily identify just from the experiment on its own. And then I guess the third probably component to our lab is we do a lot of durability work. So we'll subject different specimens to kind of aggressive chloride environments, for example, as we were talking about before, freezing and thawing, those sorts of things. So our lab has a range of these capabilities, and it's fun because each day you might work on kind of a different area.
That's great. So I'm going to pivot a little bit. There's a rumor going around, or I shouldn't say a rumor, but I believe that you currently work on the American Concrete Institute's multiple committees. From my understanding, to kind of improve design guidance for the structural engineering community and how to apply these high performance materials. Can you tell us a little bit on what that involves for you as a researcher and kind of the brain behind the materials testing?
Yes, so getting involved with the American Concrete Institute or any of these professional organizations is really rewarding and interesting experience. At a very high level, what we do is basically we synthesize kind of the state of sort of research and practice. And when we synthesize that information, we try to develop guidance on how you could design individual components or systems using the materials. And a lot of this work is still at its early stages. But what we do is we review experimental and numerical data that's been published. We talked to practicing engineers who have used these materials in the field and see kind of what their approaches were. As you can sort of probably imagine, it's sort of a somewhat slow and deliberative process. Everyone brings together their ideas so that it's done in a systematic and safe manner. If you're sort of changing the way you or the standard in which you design things, things need to be sort of taken in baby steps. But the work involves working, with other academic researchers, as well as practicing engineers, suppliers, contractors, and everyone kind of gets together to work and put their ideas to paper. And so one of the great things about being involved with ACI and similar organizations is you get to work with people who have kind of very diverse professional backgrounds, which helps you learn more and sort of critique your own work and those sorts of things. So yeah, being involved with ACI and these other professional organizations is really rewarding.
So in regards to ACI, I know right now they're at 318.19, I think is the most recent publication. And I'm not super familiar with the notes for high performance concrete in ACI. I'm more familiar with their more generic standard of, testing within 2000 PSI concrete up to 8000. Do you know when the guidance for when we would see some sort of change within ACI for high performance concrete? Is there
Sure. Yeah, I could give you kind of broad overview of how these things work. So 318 is, is a code writing body. So that's a committee that develops the code that you probably have or your colleagues do. So the work that comes out of some of these sort of emerging materials comes from other committees. So for example, there's 239 that deals with ultra high performance concrete that I'm a member of. There's 544 that deals with fiber reinforced concrete. Now these committees, don't necessarily have the ability to write codes, but what they can do is they can write design guidance documents. And so that's sort of the first step before it eventually, things could eventually make their way into higher levels. So 239 is the UHPC committee. We've published some emerging technology reports on the materials that are available to ACI members. And then right now we're working on design guidance documents. And so it takes a few years before those things sort of make their way through. But those documents, are sort of in the pipeline, so to speak. So yeah, but I imagine it'll be a while before you see it you see these sorts of materials in the 318 document that you're more familiar with.
Yeah, it's interesting to know. Yeah, you see a bunch of design guides for some of these materials, but yeah, it seems like that's the first step. Get a design guide out, and then slowly but surely, it'll eventually make it into the codes. I know they're all, I think all of them are delayed.
Yeah. Just it's the structural engineering community is deliberative and conservative group, and rightly so.
Thanks so much, Matthew. To end off here, what piece of final advice would you give to civil engineering students that are considering a career in structural engineering?
Yeah, sure. So there's you sort of get those questions a lot as like a faculty member, but there's basically two things I try to emphasize to the students. So the first is to try to make sure that life isn't just about being an engineer, and to take up hobbies that they're passionate about. So at the start of every semester, I ask my students what they wish they had more time for, and encourage them to make sure that they don't let those things sort of fall behind on the wayside. Interestingly, this semester, for the first time, I think most of my students wish they had more time for reading, which is sort of an atypical thing for engineering students. A lot just aren't readers, but that was an interesting thing I saw this most recent time. Then outside of that, in terms of professional advice, the things I try to encourage them to do is to get involved with as many sort of internship or professional experiences that they can possibly get involved with, to figure out what they're passionate about. So for example, I try to get them, or encourage them to explore opportunities in a design office, spend some time in the lab, try to be out in the field. And so that gives them a picture of how things are designed, the way they're built, and sort of what the future of structural engineering and materials engineering sort of might look like. So those are kind of the two areas I probably try to give them advice on.
Yeah, it seems like it's pretty good advice too. It's what I tell people is, yeah, there's plenty of time to do engineering in your career. You still gotta get that work-life balance in there, or else you're more than your work.
Yeah, exactly.
Yeah, and yeah, structural engineering field's very broad. There's, like you just said it, the design offices, the construction, research and lab. There's a lot of fields that you can get into.
Yeah, and I will say the exact same thing. That's great advice. I know some of our younger engineers, I'm always just kind of excited to tell them how broad,
Yeah.
structural engineering really is. You can really do anything with it, and you can go in so many directions, which I think is important, especially when you're in the weeds of education. You can feel kind of, it's always like that junior year itch where it's like you get the itch to change.
Yeah. My junior year, I had an internship and I was set, like I thought I wanted to work out in the field. And then I worked out in the field on like this union job, and I just did not, it was not for me. So then I took a summer and worked in a lab, and I realized that was something I was really passionate about. So yeah, totally get it.
Well, perfect. Well, thank you so much for your time today. Honestly, it was so great to hear about this high performance concrete. Like I said, I've just recently learned about non-ductile concrete, and now I've learned about ductile concrete. And I'm excited to hear about some of the design guidance that will come out of your research, and that we may see in future iterations of the code.
Great. Well, thank you so much.
I hope you enjoyed today's episode. We would love to hear your feedback, comments, and any questions you may have. To leave them, please visit structuralengineeringchannel.com, where you will find a summary of the key points discussed in today's episode, which is episode number 60, as well as links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe on Apple Podcasts or wherever you listen to your podcasts. Until next time, we wish you the best in all your structural engineering endeavors.